I'm going to start this video with a small experiment. I have here a triangular oscillator. What I've done is taken a broken bicycle spoke and bent it into the shape of a triangle. Now I also bent a paper clip to act as a pivot, and I'm going to let this swing by a certain number of oscillations and time it using my stopwatch here. So let me get a few oscillations going, and then I'm going to time 20 oscillations and then get the period by dividing the time I get on my stopwatch by 20. So let's start this experiment. 3, 2, 1. That's 11 seconds, 11.41 seconds. So I'm going to make a note of that for future reference. That's 11.41 seconds for a total of 20 oscillations. So the period is 20. And I have a calculator on my side. Let me work it. I get 0.57 seconds for the period. It's pretty quick. It's a quick little oscillator. Now, what we're going to do is try to verify this by the theoretical formulas that we have. So that's the reality. The reality is what you saw. And the theoretical model is we're going to think of it as a perfect equilateral triangle. You see this is not quite perfect. It's bent, and this one has got a little gap here at the end. So this is far from perfect, but this is a good model, as good as any. So the moment of inertia of an object like this pivoted about point P is given by our classic physical pendulum simple harmonic oscillation frequency formula, and that is the square root of the mass of the oscillator times the acceleration due to gravity times the distance between the pivot and the center of mass. So the center of mass is somewhere here. Then the distance d is that. So finding the distance d will be a problem that we have to engage in. And then there's a moment of inertia about the pivot point, which is another problem that we have to solve. So these are the next things that we will do. I'll take the origin to be at the pivot for simplicity and let the y-coordinate run down positive, so I don't have to worry about negative signs. Now each of these rods, each of these side rods, I'll take to have mass L and mass capital M and length capital L, so that when at the end we have to get rid of capital M, we'll remember that little m is 3 times capital M, because little m is made up of 3 of these identical rods. Now, because if it's an equilateral triangle, these angles are going to be 60 degrees, and that's the perpendicular bisector, so that's going to be 30 degrees there. So these are all geometry facts. How do we find the location of the center of mass of this rod? Well, that is this distance, and that's also 30 degrees. So that's just going to be L over 2 cosine 30 degrees, and the same for that. Now for this one, it's that distance, so it's L times cosine 30 degrees. So once we have that, it's just a simple matter to find the center of mass. The coordinate of the center of mass, which I'll call simply d, is going to be the sum of all the individual masses making up the rod, their individual y-coordinates, divided by the total mass of the rod. So let's write this out. This is going to be 2 of these, so it's going to be 2m times L over 2 cosine 30 degrees, which is that distance, plus I might actually call these something. I'll call this y sub 1, and I'll call this distance here y sub 2. Now y sub 2 is equal to, let me write down what those distances are. So y sub 1, this would be L over 2 cosine 30 degrees, and that would be L cosine 30 degrees. Just to put it all out in the picture so it looks nice. So that's m times L cosine 30 degrees divided by m plus m plus m. Okay, let's see what happens here. Here you notice that the 2 and the halves cancel out, so I get 2 times ml cosine 30 degrees divided by 3m. We'll cancel out the m's and substitute what cosine of 30 degrees is. It is root 3 over 2. So I get 2l times root 3 over 2 divided by 3. So this distance is equal to root 3 over 3 times L. So we have that useful piece of information. Our next task is to find the moment of inertia about the pivot point. Let's do that. I sub p. The moment of inertia about the pivot point is made up of 3 terms. 2 of these terms are identical because these are both rods pivoted about one end. So that's going to be 2 times the standard result for such rods is the moment of inertia of a rod pivoted about one end, which is 1/3 ml squared. Plus this one is an oddity. It's not pivoted at all, but it's floating freely in air as it oscillates. But notice that these 2 axes are parallel to each other. So we can use the parallel axis theorem to deal with the bottom rod. So that's going to be the 1/12 ml squared you would get for pivoting at about the center of mass of the bottom part, plus m times this distance, which is y2, squared. So let's work this out and see what we get. That's 2/3. I'll take ml squared outside and see what I get inside. It's 2/3 plus 1/12. Now y2 is L cosine theta. So y2 squared is L squared cosine squared theta. Okay, I've already taken the L squared outside. So now I have to deal with cosine squared theta. Cosine of theta is root 3 over 2. So cosine squared theta is going to be root 3 squared, which is 3, over 2 squared, which is 4. Okay, now we have to add the denominators, fractions, by getting a common denominator. So that's 3 4s are 12, which means that becomes an 8. That's just a 1. And then 4 3s are 12. So that's 3 times 3, 9. All right. 9 plus 9, 18 over 12. Times ml squared. Well, 6 divides nicely. So 6 3s are 18 and 6 2s are 12. Ml squared. It's now that I notice 3 times capital M is little m. So I'm going to write this as 1/2 ml squared. Now I'm ready to substitute it into the omega formula to find the frequency of oscillation. So I have here omega, simple harmonic, is equal to the square root of little m g times d, which is root 3 upon 3l, divided by 1/2 ml squared. The m's cancel out, one of the l factors cancel out, and then I have, let's see, this is 2 when it goes upstairs, and that's root 3 downstairs. 2 over root 3 g over l. Now omega is not as immediate as period because our experiment was done in seconds. So let's convert this to period. T simple harmonic is equal to 2 pi divided by omega simple harmonic. That's the relationship between the two. So I get 2 pi. I have to flip this over. So that's going to be root 3 L over 2G. Now all I have to do is substitute the numbers and see if I get the same period of 0.57 seconds. So to this end, let me measure the length of one side, since the mass does not need to be measured. It turns out the length is about 10 centimeters, so 0.1 meters is the length. So let's substitute that and see what we get. So that's the numerical work that I'm doing now. It's 2 pi square root of root 3 times 0.1 meters divided by 2 times 9.8 meters per second squared. So that's 2 pi times square root. Let me use my calculator here. So I've already done the math. Does not have a pi button, so I'm typing in pi. So I get 0.59 seconds, which is not bad at all. Now if I were a really good experimentalist, I would have done this experiment 3 times and taken the average time and then found the uncertainty in the time, and then it would have come out to be something like 0.58 plus or minus 0.03 or something like that, and then that would have covered this theoretical value nicely. So and a theoretical value is also to be taken with a grain of salt because of all this cornering, and some of these lengths may not be equal. So there's a lot of assumptions that went into this model. All that said, it's a pretty close agreement to the physical reality.